Hello, good evening. Today is September 25th. It's around 9 p.m., just after 9 p.m. Dallas time, that is United States Central Daylight Time. And I'm giving a talk on assured information sharing in the cloud for social networking applications. And this talk will be given as part of a webinar at a university in West Bengal. And that's going to be tomorrow morning, Dallas time, around 9 o'clock in the morning, September 26th. And that will be in the evening time in India. It's again part of a webinar series. And tomorrow it's going to be, that September 26th is going to be data and application security and privacy, so mainly in the data security area. And there's myself and also two colleagues who will be giving talks for this webinar. So we'll start at 7 o'clock and then another talk at 8 o'clock, and then mine I think will be around 9 o'clock, which is Central Daylight Time, which is going to be 5:30, 6:30 and 7:30 p.m. time in India. So first of all, thank you very much for inviting me to give this presentation as part of the webinar series. And I'm Bhavani Thuraisingam from the University of Texas at Dallas. And I'm very honored to give this presentation. And so it's going to last around 1 hour, but I'm hoping to give this presentation live tomorrow morning. But I've taped it just in case there is some sort of technology glitch when I give the presentation tomorrow. So I'm going to share my screen. Okay, so, right, so my screen is being shared and it's cloud-centric assured information sharing for various applications, but I'm going to focus on social media applications. Okay, so the outline of my presentation, about 5.5 years ago, we had a workshop sponsored by National Science Foundation that really started a lot of the work on big data security and privacy. So I'm first going to talk about the results of the workshop so that I can share it with a global audience. And then I'm going to talk about some example systems, in particular, cloud-centric assured information sharing, as well as secure social networking. And then I'm going to provide some directions, very briefly, data security and privacy lifecycle for IoT, trustworthy analytics. And so some of the previous speakers focused more on the data security for IoT applications, as well as data science and cybersecurity, or in particular AI and cybersecurity. So they will provide a lot more, they would have provided a lot more details of these applications. So I'm just going to briefly touch on these applications. Okay, so very briefly, the workshop, it was held at UT Dallas on September 16th and 17th, 2014. Actually, it was 6 years ago. And so we had a number of invited keynote speakers and participants, interdisciplinary research, computer and data sciences, cybersecurity researchers, social scientists, application specialists from, say, natural sciences. We had members from academia, industry, and government. There were two major objectives. One was to look at security and privacy issues for big data, and we also looked at big data management and analytics for cybersecurity. And there were keynote presentations, and then we had breakout sessions, and the results were published We submitted to the National Privacy Research Strategy, and then I presented the results to an interagency conference in Washington, D.C. in February 2015. So that was around, I would say, about 5.5 years ago. Okay, so big data management and analytics. We know that massive amounts of data are being collected, and this data is being used for a variety of applications in healthcare, in finance, but it's also being used for social networking applications, right? So tasks such as user social networking, as well as security applications. So tasks such as authentication, access control, anomaly detection, user monitoring, protection. So big data has many applications, including in cybersecurity. So we have to analyze and integrate the data collected on the web, and then we can identify various aspects such as disease outbreaks, homeland protection, and so on. So the data that we collect, even if we anonymize the data, the people can put, or adversary can put pieces of records together and infer something that is highly sensitive or highly private. So security tasks such as authentication, access control, they require lots and lots of information to be collected about users. And so if this information, say something that we use for multi-factor authentication like biometric data, if it goes to the wrong hands, then that could be a disaster, right? Especially if the information is misused or stolen. Now, examples of privacy enhanced techniques. So these include, say, data anonymization to cryptographic techniques, privacy preserving record matching. So you have multiple records, and these records could be anonymized, but we can put these records together and infer something that is highly private. So there's been some work on privacy preserving record matching and privacy preserving, various other privacy preserving techniques. So privacy preserving collaborative data analytics. So centrally collected data poses a lot of privacy and confidentiality concerns. And so you can have distributed analytics, so more distributed approaches. And so we need a lot of novel approaches in this area, also based on cloud computing. And another area that is really increasing in prominence now is privacy preserving biometric authentication. So templates of user biometric represent sensitive information. So some of the recent approaches like zero knowledge protocols. So we need some scalable techniques. And the whole idea is to minimize false positives and false negatives and ensure accuracy. So the whole area, what we came up with at the workshop, right? There are three factors here. One is, of course, we want privacy and security, right? We want to maximize privacy and security. But the question is, at what cost, right? So what about the utility? We can perturb and randomize and sort of distort the data, but then the data may be useless after that, right? So we need to take care of, we need to keep utility in mind. And the third criteria is the cost, right? So what about the cost? Because if you implement all these privacy measures and at the same time you want the data to be useful, but it could be very expensive. So it's a trade-off between utility, privacy/security, and cost. So it sort of becomes a dynamic programming problem. You want to minimize cost given utility and the risk. Of course, you need to look at the privacy risks. Another area is to maximize privacy, given the cost and utility. And you also want to maximize the utility given cost and the privacy constraints. So it becomes a dynamic programming problem. And how do you come up with this whole multi-objective framework? So that is a challenge, right? For data sharing, probability of re-identifying given certain background knowledge might be a measure of privacy risk. So that's a challenge that we are faced with. So we came up with a lot of approaches that we need to investigate. Data confidentiality for access control for big data. We need to merge a large number of access control policies. So different pieces of data would have different types of policies. How do we integrate them? How do we administer authorizations for big data? and in particular for granting permissions, need techniques to automatically grant authorization, possibly based on the user digital identity profile. Enforcing access control policies, again, the data could be, remember what big data is, right? Big data has got the 5 V's: velocity, veracity, value, volume, and there's another V, right? Veracity, volume, variety, okay, the 5 V's, right? So it's a heterogeneous, multimedia, and so on. So what sort of access control policies? And access control policies in big data stores like Hadoop, MapReduce, Spark, all of the big data technologies, and automatically designing, evolving, and managing. So these access control policies could change. So we really need evolving policies. So that's for confidentiality. For privacy, what we said, relevant issues that need to be investigated, support for both personal privacy and population privacy. So personal privacy, of course, individual privacy. Sometimes we might want to also ensure population privacy, such as people who live in a particular part of a country, you know, like say one part of Texas could have more higher incidence of diabetes. But sometimes that information is useful because you can use it to treat the population, right? So, or people in a certain area are more susceptible to COVID-19. Efficient and scalable privacy enhancing techniques. So there are lots of privacy enhancing techniques with encryption and so on, but are they efficient? Are they scalable? Usability of data privacy policies. So again, usability is very important. We often forget about the users. Users are the ones who are using the system, right? So these policies should be understood by the users. Approaches for data services monetization. Instead of selling data, organizations owning data sets can sell privacy preserving techniques on these data sets. Data publication, some are saying perhaps abandon the idea of publishing data and use the data in a controlled environment. But again, there are some challenges, right? Sometimes you might want to publish the data. Privacy implications on data quality. Of course, quality has to improve, but then when you distort the data, privacy, quality may not be there, you know, distorting data for the sake of privacy. Risk models, big data can increase privacy risks. Big data can reduce risk in many domains like national security, right? Need models for both. So, so more data, the more privacy risks, right? But you can apply big data techniques to maybe enhance privacy. So data ownership, perhaps we might want to replace who is the owner of the data, but instead talk about who is the stakeholder. There's also human factors, right? All solutions proposed for privacy and for security need to consider human involvement. And then there's a data lifecycle framework, comprehensive approach to privacy for big data. So we've come up with a nice framework, PolicyAware, data acquisition, data storage, data integration, data sharing, data analytics. I'll talk a bit about it later on. Okay, so the third aspect, of course, big data management for security. What is different about big data analytics, right? That's a machine learning. We are talking so much about AI, machine learning. These are some of the things that one of the speakers today talked about, or he would be talking tomorrow morning, actually. So the BDA for cybersecurity needs to adapt to malicious adversary. BDA for cybersecurity needs to operate high volume, high noise. They have to integrate data from host networks and media. And is there a right BDA architecture, right? Do we need different types of BDA system architectures? Should existing BDA system architectures be adapted? What about real-time analytics? And then data sharing. Cybersecurity data needs to be shared both inside organization, among organizations. So we need common languages and frameworks and infrastructures. And what about preventing attacks? Because in the end, we all want, right, the attacks, to prevent these attacks from happening in addition to detecting. So data provenance is very important, capturing the provenance throughout the life cycle of the data. So provenance-aware BDA systems, tools for cybersecurity can protect and mine useful attacker information. What about BDA for digital forensics, combining and linking different data sources? So main challenge again is to identify the right data. And then of course, BDA for understanding the users of the cyber system. BDA could be used to mine human behavior, BDA techniques could be used to understand. Again, the human is very important. What about the human aspects? So before I talk about the summary, one area that the workshop did not talk about, but that particular area has exploded, and that is what happens if the big data and machine learning and the AI techniques get attacked, right? So the adversary might learn about all our methods, right? What techniques are we using? What is our data? The adversary can thwart the data, can attack our models, and then all our data, big data techniques or machine learning techniques will be of absolutely no use, right? So we have to adapt our machine learning algorithms. We need to figure out what is the adversary up to, and we should adapt our machine learning algorithms. And that whole area has come to be known as adversarial machine learning, and that plays a major role in big data analytics and security. So what happens if the big data techniques are attacked? So that part, we did not talk about it at the workshop, but since then we've been carrying out a lot of research. And this is also one of the hottest area, I would say, one of the hottest areas in cybersecurity. Anyway, so the workshop directions: massive amounts of data being collected, stored, manipulated, analyzed, investigated the issues surrounding big data and privacy, and big data analytics for cybersecurity. And the third area, as I mentioned, cybersecurity for big data. We need scalable and practical solutions. We have to develop technologies guided by policies to address security and privacy issues. It has to happen throughout the life cycle of the data. And we need to understand not only the societal impact for data collection, use, and analysis, but also formulate appropriate laws and policies. And we need various agencies. Actually, this is sort of not just a US problem, it's a global problem. It's a problem in India, it's a problem in Europe, it's a problem in Asia, it's a problem in Australia, Africa, South America, everywhere, okay, Canada. So we need to all work together to look at big data security, investigate aspects of big data security and privacy. Okay, so that is the first part. Now, I'm going to talk about the sample systems. So I've got to keep track of the time. Okay, so I think I started around 9:06. Okay, so we have to look at the sample systems. Cloud-centric assured information sharing and secure social networking. That is my topic number 2. And these are examples of big data security and privacy. In particular, I'm talking about big data security. I'll talk a little bit as well about privacy. Okay, so we talk about assured information sharing approach. That means different organizations have to share data, right? Whether it be for, counterterrorism applications, whether it be cybersecurity applications, whether it be COVID-19 applications. So for homeland security-based applications, multiple agencies have to share data. For cybersecurity, different corporations, it'll be great if they can share their cybersecurity data, right, about various attacks. And then for COVID-19, right, wouldn't it be very helpful that if we can share information about contact tracing and testing and so on? And I was told that, I think a couple of days ago, or maybe yesterday, the British government, the NHS, the National Health Service, they have come up with an app, right, developed an app that the British people have to download, and that will tell them exactly who in their neighborhood, not who, are there people, because they've got to maintain the privacy. My understanding is that it's going to tell them, are there people in the neighborhood who might have COVID-19, or they have come into contact with people who have COVID-19. So at least you have some idea. But you don't want to give out the information about the various people, right? About the various individuals, but just the fact that there are folks nearby, people nearby, who might have been exposed to COVID-19. So that will be very useful. So what are the aspects of sharing, right? So we've done a lot of work where we looked at Medicaid claims data without the identification. How can we share data in an organization, right? Between the hospitals and the healthcare workers and so on, and the doctors' offices. But then sometimes people don't want to share the data. What are the incentives and you want to give them? And then what are the risks involved, okay? So that is assuming that the partners are fairly trustworthy. But in the real world, we have to work with people where they may not be trustworthy. So there we are using some kind of a game theoretic approach where we are working with our partners, but we cannot trust them. So we are sort of playing a game, just like what I mentioned, the adversarial machine learning, where the adversary is trying to learn about what we are doing, our data. We are trying to thwart the adversary and modifying our machine learning models. And in time, adversary will catch on to what we are doing. So it sort of becomes a game playing. The third area is active defense, because sometimes we may not be able to trust our partners at all, but we still have to work with them. And so there we want to have an edge, right? Try to figure out what our adversary is doing. So really do some intelligence gathering. So we have information sharing for all these aspects, but I just only want to talk about policy-based information sharing in the cloud. Okay, so what are the types of policies? So for example, organization 1 or agency 1 wants to share with agency 2, then I tell them, okay, we will share with you provided you also share with us. Or we'll tell them, okay, agency 1 says, I will share with you provided you don't share it with agency 3, right? So we make some agreements. So these are the policies, the information sharing policies. These are some examples. So I've got to say that our policies are fairly, simple, because we are computer scientists and we are not policy specialists. But in the real world, we have to work with policy specialists, right, to share the data. So they have to come up, policy specialists, to develop policies. So that will be more realistic policies. So right now we are working with some people in our policy, economics, policy and political science schools, some policy experts, to help us with formulating policies for data sharing. Okay. So before that we said, okay, so before we brought in the cloud, we developed a prototype, just a standalone prototype, where we had Oracle databases with our Medicaid claims data. We removed all the identification. We implemented XACML, Extensible Access Control Markup Language, for data sharing, right? For policy enforcement and policy decisions. That's part of XACML. So user poses a request, the query, and the policy enforcement point will ask the policy decision point, okay, make a decision about the policy, what we should do. Then the policy decision point will talk to all the databases, look at all the data, and then decide, and the person who is asking the questions, excuse me, and then decide whether, and then make a determination as to whether the data should be shared or not. Okay, so that is the prototype we developed. Then what we wanted to do, because when we want to go to a sort of an international setting, global setting, you can't have like standalone systems. A cloud will be very useful, because we had this joint project funded by US Air Force for us, as well as US Air Force in London funded King's College, University of London, and University of Insubria in Italy. Right, so we have policy enforcement point, policy decision point, XACML. Okay, so they funded our cloud work and developing XACML based policies. So then we started some research on the cloud. So to secure the cloud. So we had the left-hand side, sort of generic, right? Virtual machine monitor. We didn't really network monitor. We didn't really do any work on networks, but we did work on hypervisor. Virtual machine monitors like VMware or Xen. So we developed securing virtual machine monitors. On top of that, storage layer, and top of that, the data layer. And then we had the applications. Then we had policies and the quality of service, trade-offs between, security and risk and so on. So the security and data quality, remember the multi-objective framework, something similar to that. And then monitoring the clouds, machine learning algorithms for monitoring the cloud. And what about the risks, right? Risks and costs. So risk, cost versus security. Okay, so here we have all the technologies, right? So we didn't touch the network, assume that we had a virtual network monitor. And then we used actually Xen for our hypervisor. The ones in pink, they still need further work. The ones in blue, pretty much I think we have covered them. We have finished that part of the research. Then the storage is the Hadoop MapReduce framework. And then we develop multiple Hive and Sparkle query optimization. I'll talk to you all about this, the query processors, secure query processors, all of our policies in XACML. And then we also use semantic web-based policies, RDF, that is Sir Tim Berners-Lee's work, quality of service. And then we had the cloud monitors, like machine learning algorithms for the cloud to monitor, are there any attacks, right? So this was our framework. We designed and developed various pieces. Of course, it would be really nice if we can integrate all the secure pieces. But remember, we are a university. We are not a system integrator. So what we would hope is someone from the industry will come and take our technologies and sort of implement them in a large-scale fashion and do all the integration. Okay, so we developed secure query processing with Hadoop MapReduce. And in order to develop this, it was a joint project between UT Dallas, King's College, University of London, University of Insubria, Italy. So we studied cloud-based. So we said, okay, remember the information sharing? I showed you all the XACML policy managers. We wanted all the data and the policies to be in the cloud. And then through the cloud, we share the data. So I'll show you a picture later on. But in order to do that, we had to develop some cloud-based policy engines and a cloud-based secure query processor. So we developed two secure query processors, one for relational data. I will explain to you what we did. Hive is a product, relational database product by Facebook, but we Facebook implemented Hive, and then they made it open source. So we used it. We didn't implement Hive, okay? We used Hive. But we implemented a Sparkle Query Optimizer. I will talk to you for semantic web data. Why did we do semantic web data? Because not all the data is relational, right? Some of the data could be images. Remember, big data is variety. So multimedia, videos, and so on. And that type of data, we can use RDF to better represent that data. So we had two query processing prototypes, and we demonstrated with XACML based policies. Okay, and then the first demo had, so first demo was around 2013, second demo was close to 14, 15. Okay, so the first demo, we used Hive based. So our storage was Hadoop, MapReduce, and then Hive is a relational database operating in the cloud, already available open source. So what did we implement at this part here? XACML based policy engine in the cloud, sitting on top of Hive. So the query comes in, XACML policies will kick in, query is rewritten. So the major research part for us is query rewriting. Very complex actually, rewriting the queries according to the policies. And then we had XACML, right, with policy engine sitting on top of Hive. And so query is rewritten and posted against Hive, and then Hadoop will execute it and give the results back to the user. So this was our implementation, XACML. Now we wanted to go for non-relational data. Fine, non-relational data, for those of you who know about semantic web, that's Tim Berners-Lee's invention. Machine understandable web pages. So he came up with a lot of representation languages like XML, fine. But he wanted to go beyond XML, which is RDF, Resource Description Framework, much more richer than XML and representation capabilities. So we wanted to develop a policy engine for RDF. Okay, so we wanted to do something very similar, XACML, and then RDF-based policy, RDF-based database, right? Policy engine, RDF database in the cloud, and then the HDFS cloud. Unfortunately, we did not have a Hive equivalent. There were RDF databases like Jena, J-E-N-A, but they did not scale for the cloud, right? Because we are talking about billions of RDF data. RDF data is called RDF triples. So we needed something like a Hive, right? So what did we do? We developed our own, what we call Sparkle Query Optimizer. Sparkle is the query language for RDF. Data is in RDF. So we essentially built a data engine, okay, that will work in the cloud for RDF, which will take Sparkle queries, just like here, they would take SQL queries and modify, rewrite them. It will take Sparkle queries and rewrite them. Okay, so one part of it was taking the Sparkle, populating the database. So RDF triples, right? RDF is like subject, predicate, object. Taking all the RDF data and efficiently splitting the data for efficiency. On the other side, this is data pre-processing. On the other side, we are using the MapReduce framework for query rewriting and enforcing XACML-based policy engine, rewriting the query and generating execution plans and getting the data from here and then executing the query. Okay, so we had a very nice two systems, one for relational data based on Hive, and the other is RDF data in the cloud, but we did not have a Hive or equivalent, so we had to develop our own Sparkle Query Optimizer. It was a massive effort. Then we integrated both, and we had a cloud. Dallas, Texas, USA, London, UK, Insubria, Italy. So 3 organizations, actually they were universities, we pretended to be agencies, and we had relational data, we had a Hive system, and for RDF data, we had a Sparkle system, which we built ourselves. And then we demonstrated policy information sharing. So data and policies, some of the data and the policies are all in the cloud. And then when agency 1 wants data from agency 2, we look at the policies and say, okay, I'll give you this data, provided you also give me some other data. They agree, and then they share the data. And we demonstrated it, fine. Then we found that the performance was not very good. So we were trying to figure out why was this the case, right? So then we figured maybe because we are talking about policies in XACML, that's XML-based policies. And here we have data in Hive relational data. Here we have data in RDF, and the policies are in XACML. Everything became kind of, sort of like a mismatch because they're all impedance mismatch. So we said, why not have everything in RDF? Then relational data can still be in RDF. And we can also have non-relational data. We have built this great optimizer that can scale to billions of tuples for massive data. And instead of XACML-based policy engine, let's do an RDF-based policy engine in the cloud. So how do we develop an RDF-based policy engine? That's a challenge, right? In the cloud. Fortunately for us, we had built an RDF-based policy engine, not in the cloud, outside. So we use Jenna, which doesn't really scale for us for our applications, but it was really a nice system, a database management for RDF documents. We had all of the policies, ontologies, and so on in RDF. And for rules engine, rule processor, we call it inference engine. We used an open source product from University of Maryland, College Park called Pellet. And then we had interface. So this was developed under a separate project. So user is posing the query. The inference engine will look at the policies and look at the data and then modify the query and give the results to the user. It's called the inference problem. What we were trying to do is that the user, so that we'll try to prevent the user from putting lots of data together and inferring something that is highly sensitive. Okay, so what we did, we had this policy engine. So we re-implemented this policy engine in the cloud. So we had an RDF-based policy engine on the cloud, and it's not straightforward, right? You can think, okay, so we have this policy engine, we can just put the whole thing into one node of the cloud, and then we will be done. But no, that was not the case. We had to re-implement this entire policy engine with our Sparkle Query Optimizer instead of Jenna. We had to re-implement everything, right, in the cloud. So we had to look at the structure of the cloud, the Hadoop MapReduce paradigm, and then look at how our Sparkle Query Optimizer worked and took the policy engine and re-implemented it in the cloud. So that was really a huge breakthrough for us. And so now we have a much more robust information sharing system, right? Everything in RDF, 3 agencies in Dallas, London, and in Subria in Italy. We had the data preprocessor. We had the MapReduce query framework. That is these pieces, preprocessor and the MapReduce framework. And then we had the policy engine, which is this piece here. Okay, policy engine. And then we demonstrated how information was shared, and it was more flexible for us, and it also performed better, although we had multiple clouds. So data could be shared in Texas, in UK, in Italy, wherever. Okay, so this was something that we demonstrated, which was really very, very useful and very interesting. Okay, so this was funded, as I said, by the United States Air Force. Okay, now I'm going to talk some small things that we did before I go on to social network applications. So then we looked at secure storage in the hybrid cloud. So companies like IBM have been pushing hybrid cloud. That means you have public clouds that you can use, like Amazon Cloud, for your public data, and your highly sensitive data, like your healthcare, financial data, you store it in a private cloud, which is more secure. But then how do you partition the data, right? So how do you know which data to go to the public cloud, which data to go to the private cloud? You also have to look at the cost. So that is what we did some research on. How do you store the data in a hybrid cloud to support query processing, right? So we had to look at things like data costs, and how do we, the public data we may not encrypt, the private data we have to encrypt. And so what is the cost, what are the risks, and so on. So we did some nice study and implementation on secure data storage. Another thing we did also was where should we put the monitoring? Remember, hypervisor. Why do we need a hypervisor? Because there are multiple operating systems in a machine. One is called a host operating system. So if it's a Linux machine, it can also support, we can have guest operating systems for Solaris and XP and Mac OS. So who does the monitoring? Is it the hypervisor like VMware or Xen? Or should we have a monitor in each of these guest operating systems? There are pros and cons. So some of our members, they studied that, cloud integrity and forensics, right? So they did use some formal methods, inline reference monitoring techniques, and look at where are the bad guys, right? Monitoring the bad guys, one versus the other. Should the hypervisor do the monitoring, or should the operating systems do the monitoring? Each one does its own monitoring, right? There are pros and cons. Another thing that we looked at, right? So it's looking at the forensics. Another thing that we looked at is, okay, everybody's sort of raving about the cloud. Great, cloud is great for performance. So is it really true? So we wanted to validate that, right? So we took some of our machine learning algorithms, which we had implemented on standalone machines, and we re-implemented, not just take the machine learning algorithm and put it in a box. No, we re-implemented across the cloud using the MapReduce framework to see, is it better for performance? And yes, indeed, we got much better for performance implementing the machine learning algorithms in the cloud. Okay, so that was another study that we did, experimental work. And then, of course, identity management, right? I talked a lot about access control in the cloud and for data sharing, but of course, people have to be identified and authenticated. So cloud is based on web services. For web services, we use SAML, Security Assertion Markup Language, and Extensible Access Control Markup Language, okay? For identity management, so user ID and passwords. So those aspects are also important. So what do we do, right? Should we use SAML, XACML, or some other technologies? How does it work with access control or auditing? And is it one size fit all, or what are some of the challenges? But it appears today that SAML and XACML are two technologies that are being used. SAML for identification and authentication, XACML for access control. They were developed for web services, and because cloud is based on services paradigm, these technologies are being used for the cloud, and scalability has been examined. It's an issue, but still we have gotten a lot better now with respect to performance. So that's also something that we did some work. Fine. Now I'm going to talk about applications, right? How can we then share applications, right, like social networking in the cloud, and with bringing security, social networks, cloud, and big data, right? Up to this point, I was talking about cloud, security, and big data. Now we want to bring an application into this picture, which is cloud, big data, security, and social networks. First of all, I want to talk a little bit about privacy for social networks, and then I will go on to talk about security. Okay, so social networks are analyzed for several applications. We know strength of relationships, predicting future relationships, clustering, determining hidden associations, locationism. So in many cases, you know, demographics like location, a person's qualifications, a person's preferences. All of this is very important if you want to use marketing, right? What's the point to market a Dallas-based pizza company to someone living in California, right? So we really want to know the location of the person, right? But you need to have privacy and security. Sometimes people may not want to divulge their privacy. But for social media applications, we want to divulge their location. For social media applications, we want to know their location. So there is this problem between, you know, between privacy and social network analysis. So location-driven mining is really crucial for businesses. And we did some survey, it was like 5 years ago, billions of dollars being generated. But then users don't specify their location. So what we wanted to do, and we have some patents on this, a patent on this, we wanted to look at, okay, so we wanted to come up with algorithms to develop the to extract the location. So a number of algorithms, I won't go into details, algorithm called tweeted, fuzzy K closest friends with variable depth. So we looked at all the friends and where they are living, and then we are saying you are like your friend, therefore it's a very simple term, right? Very simply put. So if you are like your friend, if most of your friends are in Texas, in Dallas, then yes, your chances are you are in Dallas. But then we also take into consideration there could be movement among friends. But the point I'm trying to say is that we can use, you know, choose K closest friends. If location is not found, then we go one level further, friends of a friends, friends of a friends, and so on. But what I'm trying to say is that, okay, what I'm trying to say here is that for social media applications, we need to apply big data analytics, data mining, machine learning to figure out various properties about individuals so that companies can do appropriate marketing, right? So that's the point here. And location is a crucial aspect. So without a doubt, privacy could be violated with social media analytics, right? So what we are trying to do is to really try and find out, is this indeed a case? So we did some study. Actually, the student who did this work went and joined social media, Facebook, for a while, and he must have made enough money, so he's gone to another company now. So social media, right? Facebook is a graph, right? So we applied various data mining techniques. So we were trying to study whether a person is liberal or conservative. And while we were doing this work, MIT was also doing this work, similar work. Is the person gay or straight? So is he belonging to the LGBTQ community or not? So because MIT was doing similar type of work, it had a lot of publicity, of course, and we also got some publicity because of that work. So we looked at 167,000 profiles in the DFW, and there were 3 million links, connections, and 35,000 nodes, and testing. So we removed some details, the attributes and the various links, sometimes, you know, different ways we removed. And then to see whether can we find out whether a person is a liberal or conservative, right? So some of the data, the diameter of the largest component of the network, social network, is 16. Number of nodes is 167,000. So that many people. Friendship links is 3 million. Listed traits, over 4 million traits. These are the attributes. Unique traits, 110,000. Number of components, 18. probability liberal, because we are talking about Texas in the DFW, the probability a person is liberal is 45%, 0.45, a person is conservative is 0.55. And so we use a lot of various types of machine learning algorithms, naive Bayesian methods, so links only, average classifies based on average of the probabilities, future research, of course, we want to use more machine learning. And here are some of the liberal traits. So some obvious liberal traits we wanted to take it away, okay? Because if someone wants to legalize same-sex marriage, we know it's liberal, right? That if that person says, we must legalize same-sex marriage, or equal rights for gays, or people who cannot understand why people voted for Bush. So we did some time ago, so people were talking about Bush and George W. Bush and Obama and so on, not recent data. So some liberals said government religion is a disaster. So those obvious traits we removed. Similarly, conservative traits like Texas conservatives, we want to keep Facebook clean, protect marriage between one man and one woman. These were obviously conservative traits which we removed. And then we did some experiments. I haven't shown the experiments, it's in our paper, where we showed that, with various, so once we removed with the rest of the information, our data mining algorithms was still able to predict fairly accurately whether a person is gay or not, right? Sorry, whether a person is liberal or conservative. It's MIT who did the gay straight thing, right? So that was MIT's work. Our work was, is it conservative or is the person liberal? So that was the privacy. So we said, okay, data mining or machine learning, data analytics, it's a threat to privacy, but we need data analytics for social networks, right? Otherwise, how is Facebook going to get its money, right? So we need data analytics, and we need to have all the locations so that companies can market their products, but still we know that it's a privacy violation. So what do we do, right? So we have to work with privacy experts and social media companies and researchers, and computer scientists will have to work together to come up with some privacy solutions. Okay. Now we talk about access control, right? Access control on social networks. So what did we do there? So it's going to take me another 5 to 10 minutes and we should be done. Okay, so online social networks, access control, our approach. Current access control systems are either too restrictive, too loose, right? There's still a problem because we cannot give fine-grained access control, is still a challenge. So we use semantic web technologies to represent our social network, and then we had various types of policies. So the social network we used was FORF, friend of a friend. This is among the semantic web community. So we didn't do this experiment on Facebook. We did this experiment on FORF, friend of a friend, which is an ontology. And our application was sharing photos, photo albums, right? That was our application. So here were our policies where we said that if the target object, video of the target object, right? And the parent of Bob can determine what Bob can see. Sorry, if parent of Bob, okay, a person's parent can control what he or she views, right? If the owner of the target object is Bob, right? Then, and the photo is that of the target object. So Bob's photograph, then all Bob's friends can see the photograph. First one says that parent of Bob can control everything what he sees. The second one says that Bob's friends can see all Bob's photographs. The third one can say that if Alice is the target of the photograph, if the photograph is Alice's photograph, then all of Alice's friends can see her photograph, okay? And the fourth one is a more generic version of the other policies, right? So these policies are specified in SWIRL. And then, of course, what is our research? We take these policies and then we developed, I'll show you the architecture later, but our research is to take these policies and the query, and we have to rewrite. And it's not very straightforward. We have to rewrite the policies and the queries so that it can be most efficiently executed. So that is our challenge. Efficient execution of the queries. Okay, So this is our architecture, right? We have a reference monitor, which is that security critical component that is mediating all the requests. And we have a knowledge base. We have all of the policies are stored here. Knowledge base is our social network, which is friend of a friend, and semantic web reasoning engine like Pellet. So a social network application, reference will to request the data, reference monitor will then kick in and then look at the social network and then go to the semantic, to the reasoning engine, look at the policy, and the reasoning engine will do the reasoning and then decide should we grant access or not to the particular individual, right? So the policies, right? So in my social media, Facebook page, I can say, who should I grant access to, right? So my first level of friends, I can say they can see everything. Second level of friends can only see information about my work related stuff. Third level of friends can see even less than that. So that's what we are enforcing here. Okay, and so we had an implemented system that actually got not only the Best Paper Award at the ACM SACMAT conference, it also received the 10-year Test of Time Award last year in 2019 at the conference. So we published it in 2009 actually. Okay, so now what we are doing is, so we've got all this social networking. Remember the cloud I mentioned earlier, information sharing in the cloud, the RDF data, our policy engine, and the data Sparkle Query Optimizer. So now instead of users, can we have different social media, social networks? And we haven't implemented. We wrote a paper for a past social conference, workshop. And what we were saying was, how can we use this social media to reconstruct after a war, right? After the war or some disaster, hurricanes or fires, we want to reconstruct the country, right? Or the region. So in order to reconstruct, we are using social media. So how can we share all these policies and data in the cloud for different social network or people in one network or different networks to share data and policies in the cloud, right? So what I've talked about so far, right? NSA workshop on big data security and privacy. Then I talked about some sample systems. One was cloud-centric assured information sharing. The second was our work on secure social networking. Now, what is the future? And the previous two speakers have really, they would have talked, again, I'm recording this on September 25th, but of course I'll be live again tomorrow morning. This is just in case. And so they have given they would have given excellent presentations on data security for IoT and as well as machine learning for cybersecurity. So these are some of the applications. Security and privacy for Internet of Things. We have mobile devices, smartphones, and, we're all walking around trying to take care of your health and do exercises and so on. But imagine there's so much of privacy issues because of that, because people can know everything what we are doing. And there is this movement called quantified self among sociologists and psychologists. They are studying about people by gathering lots of information. But we privacy specialists, right, we have to be very careful, right? The private information should not be released. So data collection and sharing are being carried out in many cases without the knowledge of users. So to address this challenge, we have come up with a policy-based, privacy-aware data lifecycle framework, right? So this is sort of a high-level architecture where just in our smartphones, right, we have this framework, policy-aware. It's actually policy-aware, privacy-aware, policy-based data lifecycle for IoT. So that's the whole point here. Okay. Privacy aware, policy based, okay, data lifecycle for IoT. So we have in our smartphones, data collection, data storage, data analytics, data sharing, right? So a lot of data coming in, health data, fitness data, location, social media, image, and so on. Some data goes into the cloud for some analytics, some services, right? We may want to encrypt some of the data for backup. But what our premise here is that every operation has to be policy-based. Policies must govern how to collect data. Policies must govern how to store the data, how to analyze the data, and how to share the data, and eventually build this privacy-aware quantified self-manager. We have designed and developed pieces of this, but how do we put all of this together? Okay, so couple of charts now. Another area is, can we do things in hardware? Right, we talk a lot about machine learning. I said earlier that machine learning techniques could be attacked, right? Adversary can find out the data we are using and so on. Can we do some of these security critical operations in hardware, right? So computations over big data may require massive computational resources. Sometimes may have to use third-party servers are used for computation. And so how do we protect? One promising technology, although recently I'm hearing there are some issues, is the Intel's SGX, right? Where it has trusted execution environment. It's an encrypted secure data stream. So it can carry out trustworthy analytics. What do we mean by that? So Intel platform, SGX enabled data analytics platform is what Intel came up with. And so we have all of this, application memory, runtime, and encrypted code. And so inside the SGX enclave, we execute these data analytics algorithms. And Intel has said that these enclaves cannot be penetrated. But of course, we don't know. Like today, we know that AES 256 has not been attacked yet, but it doesn't mean somebody is not going to attack it in the future, right? So we can maybe bring Intel's trustworthy analytics platforms, right? SGX enabled data analytics platform, and then implement our machine learning algorithms. That's one solution. If we want to go the hardware route, of course, we have to do both. We have to develop both hardware solutions as well as software solutions, such as adversarial machine learning. So these are some of the directions that we are pursuing. And again, going back to the outline, I believe I've covered everything. And what I chose, since I'm going third in this series in this particular webinar, 3 lectures, I wanted to present something that would complement what my colleagues have presented. Professor Bertino, world famous cybersecurity researcher. She's a top cybersecurity researcher. And then Professor Anupam Joshi, who's also an excellent cybersecurity researcher. So they'll be talking about things like IoT and security and data and machine learning for security, AI for security. And so what I'm talking is sort of complementing what they would have presented by the time, I present it, right? So please email me or my project coordinator, Ms. Rhonda Walls, or myself if you have any questions. And so what I wanted to say was, again, it's about 10:08 Dallas time, Central Daylight Time. And so I'm going to send this link to our distinguished Professor Giri in case there is any problem with technology, so he can, show this presentation. But I will be there tomorrow morning, assuming that everything goes smoothly, the technology, I will be there, and I'm going to give this presentation again. Or if Professor Giri wants, he can, play this presentation and I can be there to answer questions. But in any case, I'm prepared to give this presentation again tomorrow morning, as well as answer questions. Tomorrow morning, our time, Dallas, Texas times, that is United States Central Daylight Time. Okay, so I'm going to stop sharing now. Right, so Central Daylight Time in Dallas, Texas, or it's going to be, that time is going to be, by the time I start my presentation, it's going to be probably anywhere between 7:30 and 8 o'clock India time, right? So around 8 p.m. Time in India. So I will see you tomorrow. That is September 26th, 8 p.m. Time in Indian time. And I will be there to give this presentation as well as to answer questions, okay? So, and again, thank you very much for listening to this presentation for the past hour. And again, any questions, please send me email. Again, thank you very much. Bye.